Hi guys, we're ready for section 5.7, which is actually going to be the last section of 5 that we complete. So it's just another example, really looking into interest and accounts more in 5.7 and how that is that exponential growth that we've seen already, but kind of putting some better equations to it, making it more just about interest and coming up with those equations that'll represent how our balance changes over time with a couple of different kinds of interest. So we're going to look at something called compound and continuous interest in this section and understand the difference between those two. And these are things that you'll see anytime you go to open an account or go to take out a loan, because you're charged interest when you take out loans too. You'll see information about the interest that you're charged and how often it's compounded or if it's continuous interest. So this is also just a good topic for life and understanding how interest is charged or how interest is given to you when you invest money. Okay, so it turns out that the type of interest we've already looked at back in 5.1 is compound interest, and it was compounded annually. So what we did there, and we're just going to put this now in terms of, instead of the y equals c times a to the x, we're going to put it specifically in terms of the investment that we're doing. Okay, so if you invest so much money, that would be like our initial value, right? So we took that initial value that we invested. And if you remember, what we did was we said, okay, we want to keep that initial investment and add in that interest rate. So we'll have R being the interest rate always in decimal form. We'll add 1 to that so we keep the original investment and add in the interest rate each time. And so that was our growth factor for the account. And then we raised that to however many years had passed. So T is going to be the number of years, where R, and this is kind of an important thing to note too, this is the annual interest rate. We're almost always given interest rate in terms of the annual interest rate. Okay, so that's why we can add that R into the growth factor and to get to C, because we're working all in the same units here. And when we do that, we take that initial amount times that growth factor to whatever power, however much time has passed. That's when we'll get out the end investment. Now you can kind of change these things around too to be also the original loan that you take out and then the end amount you would have to pay on the loan. It's just that loans work a little bit differently because we know we make payments on those loans as it's growing. So there's a more complicated scenario with loans, but if you were looking at the scenario where you weren't paying on loans, like for instance, student loans, that just gain interest over time without making any payments, this formula would work for that as well. Okay, it would be showing how your balance is growing exponentially in your loan. Kind of something that's a little depressing to think about, but something we all have to deal with. Okay, so this is the one we kind of talked about already. We're just putting an exact equation to it where we can essentially copy this process by easily changing P naught or R or T given any investment that we look at. So that's what we want to get a little practice with right now. So using that knowledge now that we had from before and this new formula to kind of summarize it all up together, we have 3 different investments to choose from. So what we want to kind of investigate here is how are those investments changing over time and how does interest rate affect those investments. So we're going to say we have $15,000 to invest. And we have 3 options, kind of some pretty normal options that you would also see in real life. So a lot of people will put their money into a checking or savings account. Now those are very safe investments, but typically their interest rates are pretty low, like around 1.2%. I think around here, the highest you can get is about 2%. Okay, so very safe investments, but the interest rates then are lower. The bank's not going to give you as much money because it's a very safe investment. Okay. And see here, we always want to think about that interest rate compared to that inflation rate we talked about in 5.6. The 1.2 isn't going to combat that typical inflation rate of 2%. So we often, if we're going to leave money in an account for a longer period of time, want that interest rate to be higher. So other options that we have, you're come across things called mutual funds. This one in particular that we're looking at earns 4% a year. Now, the only problem with mutual funds is as soon as you get away from checking accounts and savings accounts, things like mutual funds, you're investing essentially kind of in stocks, You'll have to take a financial class to kind of really understand all of that. Not even I really understand all of that yet. All I do really understand is that mutual funds are riskier. So that percentage is not guaranteed. It's something that you might be told is what they're projecting that mutual fund to make. Okay, but things like what's happening in the world right now, right? We don't know what's going to happen, and certain things like mutual funds get affected by that, especially stocks, right? That's the one we hear about all the time with the Dow Jones and things like that, right? Stocks, you never know exactly what you're going to make, but you could have one that's predicted to make a lot. This one in particular is predicted to make 12% in a year. So clearly, if we were going to invest, we want the higher interest rate. Now, what this formula doesn't take into account is that risk of possibly not getting that interest rate. But let's assume that somehow they're able to all keep these interest rates pretty reasonable for the checking account, maybe not so reasonable for the mutual fund, and especially not as reasonable for the stock to increase for 12% for 5, 10, or 20 years. But let's look and see how that interest rate affects that initial investment. Okay, if we were able to get all of those different interest rates. So using that formula up there, we'd have that we're looking for that output investment when we put $15,000 into this account. And since we're looking at a 1.2% interest rate here, these are all going to be our R values, okay? Just make sure you put them in decimal form. So here, when I plug it into the formula, I'll take 1 plus, let me zoom in a little bit so I can write this a little bit better. 1 plus 0.012 for my R, and then I'm going to test different t values in this function. Okay, so as you're plugging this into your calculator, the easier thing to do is to simplify this a little bit. That's 15,000 times 1.012, and then just take that to the 5th power, to the 10th power, and then to the 20th power. So this will be good practice for you in your calculator as well. Okay. So make sure you pause and try that, and make sure you get the same numbers. I'm going to go ahead and round to the nearest cent since we're talking about money, so to the nearest hundred. So if you plug in a t value of 5 for the 1.2% account, you'll see that after 5 years, you'll have $15,921.86. So that account would have gained $921.86 in interest in 5 years. After 10 years, we'll be up to $16,900.38 rounded to the nearest hundredth. And again, so that would mean we've gained about $1,900 in 10 years. In 20 years, we'd have $19,041.52. So if we just let our money sit in that compound interest account for 20 years, then we'll have gained about, right, $4,041.50. Okay, so what's happening there as we're looking at that, the reason this is called compound interest is because every year we get paid more and more interest, right, because we gain money the first year and then we're paid interest on that in the next year's following that as well. Okay, so give that formula a try with 4% and 12% as well. So here you should have that same $15,000 that's invested times 1.04, adding 1 plus that interest rate of 4% in decimal form to the t. And this one you should have 15,000, same amounts invested, this time 1 plus 0.12 or 1.12, which would be to the t value again. So just get used to using, again, those exponents in your calculator and compare these amounts as we go 5, 10, and 20 years into the future, thinking, okay, if we could continually get 4% on that mutual fund, how much would we have after 5, 10, and 20 years? Okay, so those are the numbers you should get for the mutual fund, the 4% account. You can see how a difference between 1.2 and 4% makes a very big difference. After 20 years, we gain about 12 or 13,000 more dollars by investing in the mutual fund. Obviously riskier though, that 4% isn't guaranteed. Okay, let's look at that stock. Okay, We had 5 years of 12% interest. Our $15,000 will become $26,435.13 in just 5 years. We've already surpassed it in 5 years what we would make in 20 years in our checking account. The higher the interest rate, the better, right? Because it makes that growth factor bigger. And as soon as we make the growth factor bigger, we know that exponential growth happens even faster. Just 10 years down the road, and we're at $46,587.72. 20 years down the road, and we really see that exponential growth. The $15,000 we originally invested would become $144,694.40. Now, like I said, stocks don't continually earn those percentages, right? This stock was predicted to earn 12% a year, probably for a year, right? They might predict a year into the future. So fairly unrealistic that you would get 12% for 20 years, but people choose really good stocks that make averages of this over several years. And so if you're good at playing the stock market, that's awesome. I, however, am very risk adverse and haven't even looked into the stock market yet. Okay, so maybe in the future I'll be more into mutual funds or something like that when I actually have money to invest. But interesting things to look at as far as interest rates go. Now, when you're looking at accounts, there's something that kind of comes up that's pretty interesting. Very specifically, I called this compound interest that was happening annually. So compound interest can be compounded, right? We're adding the interest in every year with these compound interest accounts. Some accounts or loans that you will take out will compound that interest more frequently. Okay, so we want to see what happens when we compound it compound that interest more frequently. We can do it at different intervals other than once a year. So we can compound that interest multiple times a year. When this occurs, what happens is we take that annual interest rate. We're still going to report an annual interest rate when we talk about compound interest, but we're going to take a portion then of that reported annual interest rate, which was R, and we're going to add that in for each compounded. So by that I mean, if I say I have a 5% interest rate, every time I see that percent, that's my annual interest rate. But then I'm going to follow it up with this one in particular is not compounded annually, but compounded 4 times a year, compounded quarterly. That means we would gain a portion of that interest 4 times a year. So we would just take that 5%, divide it by 4 to see that in each compounding, we will gain 1.25%. That's 5 divided by 4. Okay, so we're going to gain 5%, but in segments throughout the year. And we're going to see an example of this and how that changes the formula and how that changes the output. But what this does is it does make that investment go up faster because you're gaining interest more frequently and then getting interest on a higher balance then as this goes on. Okay, but what this does bring up is the fact that even though, right, this interest rate essentially that I'm going to get is going to change. I'm going to make more than 5% of my money in a year if it's compounded more often. That brings up a difference between APR and APY, which is a very important thing to look at in both investments and loans. So what's reported there, that 5% is the APR. It's the annual percentage rate. Okay, this is also known, you'll see it called the nominal interest rate. But we know that changes when we break up into compounding. It's actually going to charge us more if it's a loan than 5%, or we're going to make more than 5% if it's an investment. And that brings in the APY. The APY will actually tell us what we get, what we yield in a year. And it's called the effective interest rate. So even though we see the 5%, we know that we're going to make more than 5% in this investment with those multiple compoundings. And we'll see that always the APY is going to be greater than or equal to the APR. So we almost always want to make sure we find the APY when looking at investments or loans to actually know what effectively we're going to make. okay? But almost always the APR is what's reported, so you have to be careful with that, okay? So let's look at an example of this to understand why is the APY more? Why is it when we break it down, right? That percentage looks smaller. Making 1.25% 4 times, how can that be equivalent to making 5%? 5% seems so much bigger, and we just saw how much the difference was, right, between 1.2 and 4%. How can it be that 1.25% is somehow now going to end up being more than that that nominal 5% interest rate, okay? So here's what's happening. What we've done before is we've said, okay, I've got a 6% interest compounded yearly. That's what we just did, right? Let's keep this simple. We're gonna have a $100 investment and we're gonna figure out what's that worth in a year and what's that then effective interest rate. Break down that formula that we were just looking at. So the formula we were just looking at would say, okay, you can get that end amount if you take that $100 times 1 plus your interest rate, 1.06, since it's 6%. And we're only going to do this for a year. We're going to figure out how much the investment will be worth in a year. So we just take that to the first power. So right here, you can see that your actual investment in 1 year is going to get multiplied by 1.06. And that means that your APY is still 6%. You're effectively getting 6%. That's what your original investment is being multiplied by. And you would end up with $106 after a year. So if you're compounded yearly, your APY is not affected. This power is still 1 here. And you have APY equal to APR, okay? Oops, APR. But what if we just start doing it a little bit more often? What if we compound this same interest, this same account, and all we change is that we're going to compound it semi-annually? Okay, so then here's what happens. I take that 6% and it gets divided in 2 since I'm going to do it semi-annually, which means twice a year. So I'm going to get 3% interest twice a year. So thinking about this formula up here again, I can use that again to do this same idea. I'm going to take $100 and in the same year, I'm going to gain 3% on it, and then I'm going to gain 3% on that amount. So I'm going to find out what that is, and then I'm going to gain 3% again. That's what's going to happen in 1 year. So for me, just take these two and multiply them together so you can figure out what that actual growth factor we're multiplying times 100 is. If you take 1.03 times 1.03, this formula will become P equals, oops, forgot the 100. 100 times 1.0609. Notice the difference here. I'm not multiplying by 6% anymore. I'm adding in something bigger than 6% here. If I think about what that interest is that I added in, I can see right there that my APY is 0.0609 or 6.09%. I have a higher APY than my APR was reported at 6%. So what do I make in the end? Take that times 100 and you make $106.09. And you make more money the more often it's compounded. So make sure you can understand this and try this with a quarterly compounding. So same information, but compounded quarterly. So that means 4 times a year. All right, pause if you need to do that, but we're going to do it right now. So we're going to take that 6% annual, that APR, and divide it by 4 to figure out that we get 1.5% 4 times a year. So now we're going to find that end investment by taking the original investment of $100 times 1.015, that's 1.5% in decimal form plus the 1 for our formula. And we get that 4 times a year. So I get an amount and I multiply it again. I get an amount and I multiply it and add 1.5% again. So again, just focus in on this growth factor right here, the 1.015 times itself 4 times or to the 4th power. That means my $100 will actually be multiplied by 1.06136. Okay, going out with several decimals there to make sure I understand what that growth factor is. And that leaves me with an APY of 0.06136, which as a decimal is 6.136%, greater than the 6% APR that was reported. And with that compounding quarterly now, in that same year, I will make $106.14. I'll make 14 cents more than when it was just compounded once a year. Okay, so this brings up new formulas as well. We would like a formula for any amount of compoundings, any number of times a year, right? So here's our new formula for compound interest for any number of compoundings. And we're also going to come up with a formula for that APY, because so many times we're given APR. How could we come up with APY given APR? So here's your formula. What were we doing just now? We kept taking the original investment. Our new growth factor was 1 plus that annual interest rate, that APR, and we divided it by the number of compoundings per year. So here P0 is still the initial investment. R is still the interest rate as a decimal. Note that this is APR now. Okay, so understand the difference. R is always the APR, that annual interest rate. Still using that as a decimal, and we divided R by how many times we compounded a year. Oops, that was time in year is still T, but N was the number of compounds per year. P is still our final balance. Now, if we want to know what happens several years into the future, right? What do we do here? We had to multiply the power here, represented how many times for that 1 year. So we needed to take this then to the N power, but if multiple years pass, then we just do that many times for how many years. Okay, so we have the power then being how many compoundings per year times how many years do we want to look into the future. Now, if we focus in on just that growth factor, right? Remember here, we were just looking at the growth factor. We took that 1 plus the interest rate divided by the power and took it to N to figure out what that growth factor was for 1 year. So that's what we're going to use in order to come up with APY here, a formula for APY. So given R, again, given the APR, and given the number of compoundings, we can find APY if we're given APR and the number of compoundings. What we're going to do is take that growth factor, right? The growth factor was 1 plus R over N to the N power. The growth factor is just for 1 year. The T then is left alone. It's like getting the X by itself in the power. But that's a growth factor. APY is a growth rate. So we'll take our growth factor minus 1 to get to the growth rate. That would be the growth rate in decimal form. So if we want the APY in a percentage, we'll take that times 100%. So that's a formula that takes the growth factor from our compound interest formula and converts it into the growth rate that we actually effectively see, right? Our APY. All right, so let's get some practice with these new formulas. So another fairly common problem here, investing money for a long amount of time, like investing money for a new baby's education. So here we're going to use this compound interest and APY formula that we just came up with to answer this question. We're going to invest $5,000 for our baby's education. We want to know with which investment will we make the most money in 18 years, right? A lot of the time you're waiting 18 years, that's when they'll go off to college, and we want to know how much we will earn. So what I'm really investigating here is we have two things now that we know affect an investment. We know the interest rate changes how much we get in the end, and we know how many times it's compounded. So what we're trying to investigate then here is Do we want a higher interest rate, 3% versus 2.9 versus 2.8? Those are all only about a tenth off, right? Or do we want them to be compounded more often? So the highest interest rate we have here is compounded twice a year. We take off a tenth of a percent, but compound it twice as many times, right? 4 times a year. We take off another tenth, and then we're going to compound it monthly, which is 12 times a year. Okay, so you might have an idea in your head of what you think is going to be the best account here, but we're going to use the formulas to investigate that. Okay, so an interest rate of 3% here, since it's semi-annually, N is 2. So we're going to look at both the APY, what's the effective interest rate, and what's going to be that value after 18 years. Okay, we're going to look at both of those two things. So let's practice with the APY formula first. For this one, then we'll take 1 plus the interest rate. This is again the APR that's given. Okay, that's R. So 1 plus 0.03, 3% is a decimal, divided by N. Okay, that's in parentheses. We need to take that also to the N power of 2. We subtract 1 since that's the growth factor. We're at the growth rate now, and then we'll take it times 100 to make that a percentage. So, practice with that in your calculator. You need parentheses in all the places I have them, and if you put parentheses in all the places I have them, you'll be good to go. You will get the answer correctly, which is 3.0225% for this account. So it says 3%, but we're effectively getting a little bit more than 3%, right? Because we're compounding it more than once a year. Now, our compound interest formula for this to figure out the value after 18 years, that would be, okay, I want to know P. Given that I invest $5,000, I take 1 plus my interest rate again, divided by the number of compoundings, and I take that to the power of the number of compoundings times the number of years. Okay, now one thing I always see with students is your typical mistake here is make sure in your calculator you put that power in parentheses. If you don't put it in parentheses, it'll only take that factor to the second power and then just multiply that number by 8 instead of taking it to the 18th power. Okay, so make sure when you plug that into your calculator, you get this amount in the end. So after 18 years in this account, just letting it gain interest, my $5,000 will become $8,545.70. So we'll have gained a little bit more than $4,500, or sorry, $3,500 in those 18 years. All right, so do you have an idea? What do you think is going to happen? We're going to take a tenth of the percentage away, but now we're going to compound it twice as often, 4 times a year. So set up your APY, 1 plus 0.03, or sorry, nope, we've changed our interest rate, right? That should be 0.029, 4 times a year. That's then raised to the 4th power. You subtract 1 to get to that rate, and then take it times 100% to know the actual percentage. Make sure you get this same answer in your calculator. You should get 2.932%. So that APR is actually effectively 2.932%. It's higher than the 2.9% APR. Formula for finding out how much this investment is going to be worth in 18 years, 1 plus 0.029 over 4 to the 4 times 18 power. Again, make sure you put that power in parentheses in your calculator, and you should get an output here of $8,411.12. Anyone surprised by the fact that we now have a lower amount in the end, which we can actually see just in the APY, right? We know a higher effective percentage would give us more money. You can see right there before you even find the value that you know the value will be higher for that 3% account just in the APY because the APY is higher, okay? And we do see that. The difference is actually more than $100 different, right, in the end. Even though we're compounding more often, that 0.1% is proving to be a little bit more powerful than doubling the compoundings, which is a little bit surprising, I feel like, because that doubling of compoundings is doubling my power here. And that's always kind of interesting there, that that doesn't end up creating a bigger exponential growth. And in fact, that interest rate has more effect on that end amount, on that APY. We're going to investigate that a little bit more. But before we do that, let's just make sure that that trend continues, because now we're going to really up that power. We're going to make it 12 times a year. Even though we've taken off 0.2% here, we're really going to up that compounding. Let's see if that pattern continues. So here you're going to take 1 plus 0.028 this time, divided by 12 to the 12th power there, okay? Subtract 1, take it times 100%, and here you'll get an APY of 2.836%. So again, we'll see it's not going to match up to that 2.932% or that 3.0125%. We're still going to be a lower amount, even though we're compounding so many times a year. Okay, let's see how much lower by taking off those 0.2%. So $5,000 times 1 plus 0.028 divided by 12 to the, nope, not 4 anymore. It's to the 12th power times 18. See how big that power is? That's kind of crazy, right? 12 times 18 is a very large power, yet somehow we end up with $8,271.79. Yes, in fact, less than that 2.9% that was compounded 4 times a year, and that 3% that was compounded twice a year. So I want to investigate what's going on here. How is it that a power of 12 times 18 is not beating a power of 2 times 18, right? It's got to be something in this growth factor here. The other thing I really want you to realize is I feel like people, when they look at interest rates, anytime something is just off by a tenth, right? We're like, oh, those are about equivalent, right? 3% versus 2.9%. But you can see that's making a fairly big difference in the end, especially when you look at the 0.2%, right? And I feel like a lot of the time too, that accounts will try and make themselves more appealing by saying they're compounding more often, right? To try and combat that lower interest rate. But basically right now, what you're realizing is that you pretty much always want to go with that higher interest rate rather than the higher compounding. But if you, certainly if you are looking at the same interest rate, you want to go with the higher number of compoundings, so long as you are investing the money. Now, if you're taking out a loan, right, all of this gets reversed. We want the lower interest rate if we're taking out a loan, because we'd rather pay back less money than paying back more money. Okay? All right, let's keep going then. Let's try and figure out what's going on here. So I'm going to just stick with my thoughts from before, right? Okay, certainly there's a number of compoundings I can get to that will beat that 3%, right? I'll be able to take that 2.8% and eventually get up to that 3% if I just compound more and more often. So we're going to look at what happens as we compound more and more often. Does our money go off to infinity as we just change these compoundings? So we're going to make this really simple. We're going to invest $1 at 100% interest rate, so that we have a bunch of ones we're plugging into the formula essentially, right? So if I'm thinking about my P equals P naught times 1 plus R over N to the NT power, we're going to look at what happens after 1 year. So T is 1. I don't know what's happening here. There we go. We're going to look at 1 year, an R value of 1, and an investment of $1. So basically that simplifies it all down, right? That's 1, that's 1, that's 1. And so we're just looking at our end amount being this formula right here. 1 plus 1 over N to the N power. We're going to see what happens to that dollar over time. Okay? So I'm going to do this though by investigating what's happening within. So the interesting thing here is we would expect exponential growth, right, as n goes off to infinity because we've got n in our power. But n also shows up in the growth factor itself. So let's investigate first what's happening with this 1 over n as n goes off to infinity. So if we take 1 over n and we start upping the amount of times, 100 times a year, 1,000 times a year, we're getting to this idea that we're compounding continuously. And we're essentially compounding as fast as we humanly possibly can, as fast as a computer can compound that interest. As soon as you gain interest, you have that amount, you already have that interest in your account, and you just keep gaining interest on that interest, okay? That's what we're looking at here. So think about what's happening, first of all, to that 1 over n and the growth factor. So as I keep dividing by my interest rate by the number of times I'm compounding, something interesting happens here. 1 over 100, I'm adding in 0.01 with each compounding. 1 over 1,000, and now I'm adding in only 0.001 with each compounding. 1 over 10,000, and I'm adding only in 0.0001. 1 over 100,000, and I've got 0.00001. So this is going off as n gets bigger and bigger. It goes off to 0. It's like as I'm compounding more and more often, I'm almost not adding anything in to the growth factor. That growth factor was 1.01, but it starts to then, right, where is this growth factor going? This growth factor itself is approaching 1. And what happens as you take 1 to a power? Well, 1 to a power, if I take 1.01 to the 100th power, I see that exponential growth. I'm actually seeing an effective interest rate, right, of much greater than 1. But I'm not seeing it get bigger and bigger as n goes off to infinity because my base, my growth factor, is approaching 1. And I know 1 to any power is just itself. And so what we see happening here, as you plug these numbers in, you can do this along with me in your calculator. These numbers start to level off. We start to get closer and closer to 1 in our growth factor, and we don't see that exponential growth anymore because of the fact that 1 to any power is just itself. So these numbers are growing, but they're growing very slowly at the end, and you can really see that growth slow down here. We're down to the same thousandth here. So that exponential function that we have does not behave in that exponential manner that we would expect. We would expect that in our power that's changing to grow exponentially, we expect it to grow exponentially. But what do we see? That long-term behavior of our exponential function, it levels off. And have you guys ever heard of that E before? It's kind of like pi, right? It's just a number. That's this number you're seeing right here. It levels off at about 2.718. And that if we continue on to see what that number approaches, if we kept taking higher and higher powers of n here, we would get to that irrational number E. If you hit E in your calculator, which if you're looking at a graphing calculator, E is by the division sign or by the LN button on the left-hand side. If you hit E in your calculator, that number we eventually level off to is 2.718281828 and so on, okay? So that's where E comes from. It's that number we approach basically when we're having division combating that exponential increase in the same equation. So interesting there, okay? So that number of compoundings, no matter how many times you do it, even if you do it continuously, you're not going to see that exponential growth by just changing the compoundings. You would have to increase the interest rate to see more money. Okay, so somehow this E then will represent continuous compounding for us. And the way that E is going to work is it's going to be a power of E that gives us that APY that we'll actually see with compounding continuously. So let's do another experiment. This time we're going to raise it to 4%. So if I take 1 plus 4% and I change up those compoundings, what does that growth factor approach? So if you plug in 10, you should get 1.0407277734. It goes on for a while. You do it 100 times, again, you're going to see that approaching a constant value. 1,000 times, and you really see that approach into 1.0408 and so on. Now in your calculator, evaluate E to that interest rate. E to the 0.04, and that's exactly what we're approaching. That is 1.0408, 10774. As we increased N, that would be the number we're going to. So that E is very powerful. E to the R, what you're seeing right now, is the same thing as this as N goes off to be continuously compounded. So that's going to be our new growth factor for when we want to compound continuously. So we're going to take this part of our compounding formula and just replace it with E to the R. So it actually turns out the compounding continuous formula is a little bit simpler. It's still going to be, right, if we're just replacing that middle part, we still have P equals P naught, but now our whole growth factor there is just E to the R, and the growth factor then is taken to the T power for time passing. So this is our formula for continuous growth, where P naught is still the initial investment, R is still the APR, T is time in years, and P is still the final balance. E is a constant. It is not a variable. It is just a constant you can use in your calculator. That means we have a slightly new formula for APY, right? We have that interest rate, that R, APR that we're given, but if we have a compounding continuously account, then we take that growth factor -1 to get to the growth rate times 100% to know what that effective rate is. Okay, so let's get a little bit of practice with this. So now let's compare. Now you should know if you're offered a 5% account compounded semi-annually versus a 4.5% account compounded continuously, you should be able to tell me right now which one you assume is going to be better. It's going to be the 5%, the higher interest rate, even though it's compounded only twice a year versus essentially infinitely many times in a year. Okay, but let's see exactly how we know which investment is better. So one thing that we talked about before, here I'm like, oh, I can't use my formulas, right? I don't have an initial investment. What do? I don't need that, because in order to determine which investment is better, all I need to do is just compare APY. Okay, we're going to get one more practice here with APY and using APY to compare investments. So the first account was 5% where N equaled 2. Now because I have an N value here, I am using the growth factor from my compounding accounts. 1 plus R over N to the N power, subtract 1 and multiply by 100%. Okay, so in your calculator here, you'll have a couple parentheses. You'll take 1 plus 0.05 divided by 2, raise that to the second power, subtract 1, close your parenthesis, and multiply by 100. You should get 5.0625% for the 5% account that's compounded semi-annually. For the 4.5% account that is compounded continuously, so here's the deal. You'll still see that compounded in the sentence, right? It's compounded continuously. But as soon as you see continuously, you know you have to work with the formulas that contain E. There's nothing to plug in for n here. We must be using these formulas as soon as we see continuous or continuously. Okay, so I need my APY formula for compounding continuously. That is e to the r, start with a parenthesis, e to the r minus 1 times 100%. Easier to plug in. Find that e in your calculator. Parenthesis, take that e to the 0.045 to that interest rate, minus 1 times 100%. Getting practice with that e in your calculator, you should get here 4.6028%. Okay, so which investment is better? 5% is better because the APY is greater than the APY of the other account. Now, I do want to make a very important note here, right? We've talked a lot about investments today. Loans, if you're taking out a loan, you want the lower interest rate. So if I was asking you to choose between these two accounts and you were taking out a loan, you would choose this one. If you were taking out a loan and you would choose this one, you want the higher interest rate if you're doing an investment. If you're doing an investment, you get that higher amount in the end, right? That 5% makes the account grow faster. If you're taking out a loan, that means you're going to have to pay back more money in the end. So you want it to grow slower and you want that lower interest rate and less compounding. Okay? All right. Hopefully that helps you guys with your homework. You're going to get a lot of practice with these formulas, but reach out if you have questions. All right? Hope to hear from you guys soon.